Welcome to Impact Live. I'm your host, Geoff Matthews. Today we're speaking to Leo Crasti from Enviro Australis, a company that has been challenging Australia's stormwater status quo for more than a decade. Now you might be thinking, why are we even debating this? Surely using the rain that falls freely from the sky and rushes down our streets is a no-brainer. But it's not that simple. Firstly, you never know when you're going to get it or how much of it. And stormwater runoff picks up all sorts of pollutants, oils, sediments, heavy metals, plastics and microplastics. And that means we need to treat it. The moment you start treating it, of course, you need to collect it, move it, store it, filter it. And that's where the complexity and the cost traditionally kick in. There have been many attempts, and there still are, to turn stormwater into a reliable, renewable resource. But Leo's technology takes a very different approach. It solves problems that have held this industry back for years, and it may well change the economic equation behind why we currently allow billions of litres of stormwater to flow almost untreated into our oceans where it causes real environmental harm. Leo, welcome to Impact Live.
Thank you for inviting me. I look forward to it.
Thank you. Now look, stormwater being a renewable resource, it sounds like, well, a no-brainer, we should be doing it. Tell us what Enviro Australis does and what's different about your unit and how it can help turn the economics of stormwater around so it can be a renewable resource.
Well, thank you. That's actually 3 questions in one. Let me see if I go back over that. So what does Enviro do? We have developed systems that can be installed in stormwater drains. These systems are rated to suit the different sizes and flow rates. And one single system can remove the trash, litter, sediment, nutrients, separate the oils, take out the toxic chemicals, and hold that for a period of up to even 12 months, and then be serviced and removed in a controlled manner. So effectively, the water that's flowing out of our device is clean and sustainable.
This sounds like black magic in this box, and I've seen the size of these boxes, and we'll put a picture of one up. I mean, these are a big infrastructure, concrete units, and you use hydraulic separation to do this. But what I find mind-boggling is down to the particle size that you can take out without any filters or media or meshes or anything to do it. You're doing it by using the volume of the water and the gravity, the energy in the water to do its own separation. Is that correct?
That is correct. And in fact, it's actually not black magic. The fundamentals of it have been around for a long time. So the principle that we worked on is that, and by the way, that picture that you're throwing up there, you're talking about a system that processes 5,000 litres per second. And you're right, no filters, there's no media. So I'll try to explain the principle without going into super technical detail. The principle is simple. You take sediment, for example. We know that when sediment settles, that its mass is greater than water. And therefore, the question I asked myself years ago was, why doesn't that sediment settle directly to the bottom of a bucket or a vessel? The answer to that lies in the fact that there's a complex affinity between water and particulate matter, and that's why we have the term that says totally suspended solids. So what is happening is that at a level of size of below 500 microns, particles have a relationship with water. What we are doing in our device is to disrupt that relationship, allowing the material to settle and gravity to take over, and then we allow that material to settle into a lower sump, and therefore it's out of the flow area, the flow zone, and it sits there quietly awaiting for extraction. So it is a principle that's been around for quite some time, but it took somewhat 6 months of study on my behalf to try and understand that affinity and how to break that affinity. So that is at the core of the process.
Again, my mind boggles at trying to get down to that size particle matter it separates. So it first comes into a chamber, and the stuff that floats, that's quite easy to separate off, isn't it? The bigger stuff and the stuff that floats.
Yes. Well, now you've picked on a unique feature. We actually separate the fine material first and allow the bigger, more buoyant material to be pushed into a second chamber where it's held, and we prevent that material from churning and breaking down. And if you think about it, down the drain goes a piece of cardboard, for example, or litter. It takes time for that to get wet, but when it gets wet, if you've ever tried to pick up a wet piece of cardboard out of a bucket, it suddenly breaks up. So the last thing we want to do is to allow that to churn. So we separate out that buoyant material, push it into a second chamber, and then the finer particles are settling down. And the analogy that I use is similar to vertical blinds. So, Geoff, if I show my hands as an example of a vertical blind and I'm looking to you, then
Yes,
I see you and you see me. Now, if I turn the blinds, then it reaches a point where you don't see me. But if I then move around and look through the blinds, we get to see each other again. So the
yes,
principle that we've applied here is that we allow the water to slip through the blinds, whereas the particle, which is much larger relative to a water molecule, goes past. Because anything that has size has mass. Anything that has mass has inertia. And of course, the relative size between a water molecule and a particle is like a baseball to a house. The relative size is massive. So that's where we interrupt that affinity and allow the particle to then travel in its own little course. Gravity takes over and it ends up in the sun, held quietly there for the next service to occur.
right. Just this word quietly, because that's how traditionally we've got things to settle. Settling ponds, for example, we put fluid in, and over time it settles. Yours are pushing out what 5,000 litres. Whatever's coming in is going out the other side.
Correct.
So it is the speed and the volume and the energy of that water that 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 is the question I've got. That's a bit my mind is boggling at this volume of water because I've been in a lot of white water myself, and trying to understand how you're using that mechanics to actually separate down to that finer particle removed. Because when I want to put up a chart so people can understand my brain's confusion, and maybe that's why I'm trying to get it out of you. And I put up a chart of how fine a particle matters that you can separate out to, and how much you take out while this thing's flowing at let's call it full bore. And
Yes.
and that's the bit that's the black magic to me. And I just want you to sort of, if you can take the layman in me through this process of how you get it out to that level while the thing's
Okay.
still pumping. It's not a settling pond.
Rather than trying to get into complicated affinity hydraulics, let me answer it a different way. Included in our technical manual, we actually disclose the work that was done by Sydney University. So what I had to do was to take it to a totally independent authority, and that was the civil school at Sydney Uni, which is absolutely preeminent, unquestionable. And over a period of about 6 or 8 months, a student, together with supervision, studied the process, and we gave them access to a scaled down model where they could push it to its limits. And what they confirmed, they applied some theory that had been around for some time. It's Bohr theory and all sorts of things. And inside that report, they demonstrated that if we've got an aperture, and say that the aperture we're looking at is 500 microns, what we are doing is reliably removing something which is down to 20% of that aperture size. And that is because the aperture is side on, parallel to the flow, which means the water is flowing past that aperture, not through it. Hence the reason why you're challenging or questioning that process, because you are right. If we run 5,000 litres a second through a screen and push it straight through, the logic is that it will clog instantly, pretty much instantly. But what we're doing is running the water past the screen. And what that is doing is allowing the water to slip through. and causing the particles to then lose that contact with the water, and then they actually don't settle. It's probably the wrong term. It falls under gravity. It just happens to be a bit slower because it's falling through water than falling through air. So it's a bit like unlocking that umbilical cord, so to speak, with its carrier. It's now undone. Right, I'm free to fall now, and the particle drops to the bottom. And it drops fairly quickly. It's surprising, but we encourage the dropping action, and I'm now getting into the deep IP of it, because we not only are moving the water past the screen at parallel, but we're causing a horizontal rolling action to occur. It's not a vortex, but it is a rolling action. So whilst the particle is falling, we then dump it effectively into the bottom of the sump. So there's two actions. We disassociate it from its hydraulic connection to water, and then we dump it into the bottom zone. And that's where it's accelerating the process, because quite often settling ponds may take, theoretically, even days for particles to settle out, whereas we're doing it in seconds. And there is a sweet spot, and I don't particularly want to venture down too far there, but there is a fairly complicated, and in that report that's written by Sydney Uni, we disclose the formula. So we're the only system that I'm aware of on the planet that actually has a formula where we can predict the internal hydraulic action of the separation process.
Would there be a minimum flow and a maximum flow?
Very good question, Geoff. There actually isn't a minimum size, but there is a maximum, and that maximum is part of the design. When we are specifying a system, we do look at the maximum flow rate. So in general terms, we would consider that 2 litres per second of water velocity coming in is about the maximum velocity. So it's not really the volume of water, it is that velocity entering our system. Because when it enters, we change the nature of it from being a parabolic flow, in other words, flows faster in the center of a pipe, to a more laminar flow, and then cause this hydraulic separation to occur. So there is a total of about 4 or 5 actions that are occurring simultaneously inside the device that is causing all of this to work and work basically seamlessly, and it just happens. The testing that was conducted at Manly Hydraulics after university pushed the item to 200 litres per second in a relatively small unit. They tried to make it fail. We threw mud at it. It was where the particle size distribution was 97%, whatever the numbers are in the tech spec, below 500 microns. That's half a millimetre in size. We successfully removed 80 to 86% of everything below 500 microns, right down to 20 microns. And that was done independent of us. It was done by authorities. They ran it, they pushed it, they never serviced it. And after about something like 32 or 38 effective rainfall events, which is equivalent to 2 years in operation, it was still fully functional.
Your lifespan of these things is like 100 years. So I'm assuming there's no moving parts inside either.
Correct. It's all static. It's manufactured from marine grade stainless steel. That's the internals. If we apply the normal life cycle degradation rate, technically, theoretically, the internals have got a 1,200-year service life. The externals are made from green concrete, where, based on Australian codes, they're well over 100 years. I mean, reinforced concrete's been around for 3,000 years. The oldest structure's been around for 2,000 or 3,000 years. So we're not frightened of making that claim and setting it out with our warranty statements. And I also support that with personal professionally indemnity insurance.
Yes, and I see you're using some repoly fibres as well in your concrete, which is Dambar Plastics fibre division. We know them well, and
Yes.
and that concrete be recyclable. Everything in there, stainless steel and concrete, 100% recyclable at the end of that as well.
It is, and the calculations that we've done suggest that we're taking the equivalent of the entire single household, 1 year's worth of polypropylene that gets thrown out in the bin. We are sequestering that back in the concrete and are displacing the need for steel. Steel is a major contributor to CO2. So we're removing the amount of carbon dioxide that we generate, we're recycling it, And we're also using NDIS in the manufacturing process. It's also lower energy in the manufacturing process because we don't have to worry about cutting, folding, and processing steel reinforcement. And we don't have the chemical attack problem because reinforced concrete is great, but you must make sure that the steel is chemically isolated. With polypropylene fiber, we don't need to worry about that. So we're able to
Yes.
produce a lighter structure, and that in turn evolves into lower energy of transport, lower energy to install. The whole aim of this is to make it increasingly more sustainable. And at the end of its life, if it happens to have an end of life, you pull it out, crush it, regrind it, and reuse it. We don't
Yes.
have to go and make new concrete.
Yes. And at the SIMPAC Live Sustainability Awards, which you won the award for managing water resources, congratulations. You told a story, and this also had an effect on me, about you installing one of these. I think it might have been at a service station or some where there are diesel pumps, and there's obviously petroleum products that were always going to get washed down into the stormwater system. And the water testing showed there was nothing detectable after it came out of your system.
Yes, well, that process was undisclosed to us. It is a service station in Brisbane on the way to the Gold Coast. And we installed the system, and about 12 odd months later, I had a phone call from a civil engineer. And this girl rang me and said, "Oh, Leo, we've done a water analysis of your system." And there was a quiet pause, and I'm thinking, "Oh dear." She said, "It's all right, Leo. We couldn't find anything in it." Really? She said, "Yes, I'll send you the NATA report from ALS Laboratories." And they analysed that water sample down to parts per billion and could not detect any of the total petroleum hydrocarbon chains or any of the other pollutants that is typically in stormwater. So, in effect, it's a zero result. So that is stormwater flowing off a service station through a device, and that water was clean enough that you could have drunk it.
Right. Okay. So let's now look. You make these devices. We've talked about how it has no moving parts, no media, no replaceable bits. It collects stuff. You can suck it out with a pump truck
Yes.
whenever that requires once a year or something. You've installed now what 400 of these in Australia?
Well, our latest estimate is exceed 600 sites operating around Australia.
600 sites now. Wow, cool. And from all sizes, we've seen the big sizes down to the small sizes. But you think that we're only scratching the surface with 600 sites, and with the amount of volume of water that we could, that we could be saving, but B, we're going to be paying a lot of money to have this amount of water available to us because everything is water hungry. And
Yes.
as you point out, there's desal plants. We've had people talk about desal plants here on this program, and water is a scarce resource and it's an expensive resource.
Yes.
And we
Can
could
I
be doing
dive in
things
there,
a
please,
different
Geoff?
way.
I've got to dive in there because this is where our whole mission started. And I go back to my dear late dad. As a farmer, he said, "The rain comes out of the sky, it's free." And here in the city environments, the urban environments, rain falls onto the city environment for free. We then spend literally billions of dollars piping that away and disposing of it into waterways in the ocean. My estimate is that we're dumping 130 million tonnes of pollutants into the world's oceans every year. United Nations are aware of that figure and no one's disputed that. So after doing away with the free resource and transporting pollutants out that's destroying biodiversity, we then spend another lot of billions of dollars creating dams, desal plants, and bringing it back again. Our mission, our next stage of our mission, is to provide a system whereby we capture that stormwater locally, we create decentralisation asset locations where the stormwater is captured, it's cleaned, it's disinfected, and made available. And we have analysed that there's a sweet spot of around 30 homes. In fact, we've analysed roadways 1 kilometre of roadway could capture enough water to neutralise the heat island effect and provide around 200 to 400 litres per day of water to the next 30 houses around that 1 kilometre of roadway. Those are the sorts of numbers that are available, and our cost estimates are showing that that could be a lower cost than corporation water.
Yes, and new developments, new roading, we're putting a lot in all the time. We should be thinking about harnessing that stormwater. And in terms of cost, this has got to be cheaper than letting it, as I said, letting it flow out into the ocean and then trying to invent a way that we can bring it back or save it in another form.
Correct. It has to be, because we would then avoid all of that huge infrastructure. Every street that we drive on has got stormwater pipes buried below it. Every time you see a curbside and a slot or a gap in the drain, below that is a stormwater pipe. So fundamentally, you're basically saying that every metre of street equals another metre of stormwater drainage. That's the massiveness of the infrastructure. It's the same cost as the roadways. It is mind-boggling.
Yes. So let's come down to what's stopping this. I mean, you're not in startup phase. 600 units are out there and operating. It's a proven business case. You must have proven costs. And what's stopping it being implemented more widely and more widespread?
Well, to summarise that, there's always the old resistance to change. There is currently infrastructure, there's currently practice, and so on. So we've got to break into that endless chain of, oh, this is how we do it. There is also the other complexity that water is supplied to the Australian population in cities at a subsidised price. I mean, we generally pay around $3, maybe $4 per kilolitre. That's 1,000 litres of water, and it's only $3 or $4. There is no way that that recovers the cost of the infrastructure. So what our aim next is to get together with the water authorities and the influencers and to enter into some form of collaboration or partnership so that we can then have our systems offset the core asset value at the start. And you're right when you talked about new developments, that's our starting point. But we're also focusing on what's been out there, because there is old infrastructure, old stormwater systems that are currently not functioning. We've got on-site detention requirements and so on. We think that there's an opportunity to now wind back and to look at retrofitting and saving the cost of rebuilding old infrastructure. So there's a two-pronged approach, and we've got to be a bit patient. I respect that. But at the same time, urgency is required, because climate change and the need for sustainable water won't wait around for us to catch up with bureaucratic process and politics. So if anyone's listening to this interview later on and understands the dilemma, we're really anxious to talk to them and to analyse that cost benefit and the implementation process.
Now, do you find, I find this across a number of industries, that the procurement process we currently have across industry, local government, it favours the status quo. And as we're trying to move away from fossil fuels and become more sustainable, it's ironic that a lot of these fossil fuels, like roadways and things, you bring a better version to say, well, that's not in our specs. Do you find that this is getting a difficulty in breaking through that procurement, those barriers, and getting inside the specifications so it's allowable to be bought?
Look, it is difficult, and it has been. However, I think we're seeing a shift, and that shift is actually coming from a new generation. People a lot younger than myself, for example. I've been an engineer for 50 odd years, and I've seen a huge change in the attitude of technical people. The new professional coming through understands sustainability more than I think my generation earlier on did. And the case in point, for example, is solar panels. Nowadays, there's no resistance to solar panels. We've got electric vehicles. This resistance to that is diminishing. So we're actually at the start of a phase of change with water as well. So we have the inertia to change, yes, but I also think that we've got a new generation of people in the professional sector who are prepared to prosecute our argument and to listen. And that's why it's our responsibility to provide them with a nice, simple story, I think is the right term to use, that explains the benefit and explains that we're in a position to help them implement it and not just leave it up to them. So we want to be part of the process. We'll work with governments and local authorities to implement.
So, Leo, have you got any idea of the life cycle cost versus other competitors in the marketplace, given this product can sit in the ground for 100 years? And
Yes. We do, Geoff, and I've got to be a little bit careful to make sure that we're not treading on other people's toes because we need to be respectful of the market. Our analysis, and we are able to disclose that analysis to anyone, clearly demonstrates that we are somewhere between 40 to 80% lower cost to own than anything else that we see in the marketplace. And that's driven by the simple fundamentals that our systems are easy to install. It's a plug and play. Even a big system like that, 5,000 litres per second, it only took hours to install. Once it's installed, it operates. No consumables, no components to replace. It's a matter of a vac truck once a year, and that goes on for its whole life. So we can substantiate that. So in summary, we are substantially lower cost. In fact, some of our ROIs are suggesting that the value of our system at the start would be recovered in 3 to 5 years based on just the saving in maintenance cost and service alone.
and I know you were just talking about maintenance then and ROI and cost, but what about the ROI compared to having to buy that water from elsewhere?
The numbers there are actually very favourable. If we take the $3 to $4 per kilolitre and create an equivalent calculation where the infrastructure is subsidised, one of the numbers that we ran a couple of years ago suggested that we could do that for under $1 a kilolitre. So that's around a third of the cost of corporation water. The reason for that saving is that we discount all of that infrastructure of taking the water away, which, as I said, comes for free in the first place. We then eliminate the need to bring more infrastructure in on the supply side. And if we stand back and evaluate the value benefit of eliminating all of that work and put that down to the actual product, i.e. water supply to the household, it was something in the order of 80 to 90 cents per kilolitre.
Let's just say you've got this stormwater pipe under your street, and you can retrofit your unit in, dirty water going in, clean water coming out. How are you going to use that water? How are you going to get it back up into the street and use it for the households or whatever we want to use it for?
Very good question, Geoff. Okay, so the principle is, let's take a new estate as the example, then we'll go back to the retrofit because you just mentioned retro. New estate, roads are going to be built, there's car parks, there's all sorts. Our principle is the stormwater is flowing underground in a pipe. We install one of our devices, cleans all the water up. We then build an underground storage tank effectively. That storage tank is manufactured again from green concrete. That could be 500,000 litres, 1,000,000 litres or more, depending on the size and nature of the area. We also include in that a disinfection process, which makes sure that any pathogens that may have got picked up from the street are also processed. That can be solar powered. That water is then either made available by pressure pump through the normal process, irrigation lines, or the alternate way to do it is to use solar energy again during daylight hours when energy is basically there for free in Australia. We pump it up to header tanks and that becomes available for irrigation. Second, pipe work into houses, flushes toilets, washes clothes, all of those other things, because we only use around 20 to 40 litres per day per household in the kitchen for drinking, preparing food and so on. make that corporation water. The rest of the water, we can supply that. So as I say, 200 to 400 litres per household per day through that infrastructure. Retrofitted, similar process, a little bit of extra design work required to work out how it fits into the system, but it's a similar arrangement again. Bring the pipework together, clean the water up, store it, keep it underground where it's nice and cool, it's not going to evaporate, and then allow it to infiltrate back into the soil through irrigation and these other reuse processes.
And I would also imagine that in places where we're trying to get green corridors and we're trying to, put vegetation in to try and help cooling of our cities down and things, having this clean water available under our streets could also, be the lifeline for these green corridors.
Look, absolutely. And of course, we talk about the heat island effect. It's a no-brainer. We have to do it. But imagine roadways that are green on each side. We're also minimising the amount of carbon dioxide that's discharged, because green environment not only cools, but we're soaking up the CO2 and converting it into oxygen. We're making a roadway a corridor for clean air to flow, rather than having stale air that's hot and awful. We all know when we're walking down, we're taking the dog for a walk. Where are you going to go for a walk? You're not going to, if you've got a nice green patch with trees, you're going to go for a walk there naturally. Human nature tells us that that's where we want to be, not in an open plain that's just covered in concrete. It's hot and bothered, and we just don't feel right as human beings. It just brings us back to nature, and it's sustainable.
No, absolutely. I want to talk about scalability. So, manufacturing concrete in one location and hauling it around, not that efficient. Are you going to look at, or do you even manufacture in different states, depending on where your orders are coming from?
We are decentralising, Geoff. We do have a global model. I don't want to go too far down it at this stage, but the entire process is designed to be decentralised. That includes the design of our internal processing components. I remember an individual a few years ago equated us to IKEA, basically flat packed. So we started off this process imagining how we could supply our systems to the world. So it is designed to be decentralised. Here in Australia, we're supplying Australia mostly from one location, but now we've got second locations that we're decentralising further. But for the global markets, we already have the mechanism in place to be able to have our systems manufactured locally at the local economy value, so that people in, say, India or Southeast Asia or Africa are going to have these systems at their local price, at their local cost, and not at some inflated import value.
Yes. Good Australian technology developed in South Australia, exported to the world. That would be a great story.
That's our story. It's coming soon.
Look, thank you so much, Leo. That's all the questions I had for you. If any of the audience that is watching have got any questions, you can put them into the chat now, and Leo and I will be online for the next 20 minutes or so, and we'll answer any of your questions. Thanks for coming on the show, Leo.
Pleasure. Thank you very much, Geoff.